All right, so we started talking about non-smooth but convex optimization. The first thing we talked about was this idea of subgradient. So we want to replace the gradient vector we have been using with some good substitutes. And I don't have the gradient because I don't have derivative anymore if it is not differentiable. So what was the definition? This guy, V, is a subgradient if you take your x, it's a subgradient at x. You take your x and you take any other y in the domain, you look at their difference. The difference is got to be bigger than that vector times y minus x. So this is imitating the inequality you get with the gradient vector if it was differentiable and convex, okay? So this is definition of a subgradient vector. And there is not only one of them, there's a collection of them. Okay? So actually I put an exercise when I was putting the video. So we discussed this like 20 minutes or so last lecture. I just put it on Canvas today and I put only one exercise, which was if you take this definition and if you say just for sanity check, let me go apply it on something that is actually differentiable. What do I get? You get back only a gradient vector. Okay, in the case this is differentiable, a subgradient, there's like the subgradient, which is the gradient vector. Okay, but in the case that it is not differentiable, you get a collection of options. And we reasoned through this last time, and one way to see it is this geometrically, if you would like to see things geometrically. So if you draw the epigraph of your function, if it is convex, the epigraph will look convex, just like this guy right here. What was the epigraph? You take your x, you go to fx, and you put everything bigger than that, right? A convex function will give you a convex shape when you do that. This is equivalent we discussed some time ago. If you forget, it's okay. You can go look. So you'll get such a convex shape. And then what you do now to go from, say, xfx to another point, say y fy. So the difference here looks like this, right? Y minus x, fy minus fx. Right? And if you look at the inequality, it says take this part, multiplied with your vector v, and that's got to be less than fy minus fx. Right? So if I write it some other way, the inequality says the following. For my v, I have to have, let me see which 0 bigger than fx, fy plus v transpose y minus x. I'm just rewriting this inequality. This is what that thing is saying. So what you do, you say, I think about the vector v next to it, a minus 1. And if you take this v minus 1, and if you dot product it with this guy, you literally get the expression right here. That means that dot product has got to be like a negative number. That's what characterizes the subgradients. So geometrically, you need to get a vector when you dot product it. The dot product with this guy has got to be a negative thing. Now think about what kind of vectors will give you a dot product with this particular one negative. Well, you know, it will be like a cut here, above positive, below negative. However, you are allowed to pick any y you like. It's just one of those vectors. You have to have the same thing for all vectors to be a subgradient. Okay? And you end up going back to this normal descent cone we discussed before. Geometrically, being a subgradient for v, the notation they use this. Now this used to be a partial derivative. Now they use it for this subgradient set. Don't ask me who invented this. I don't think it's a great notation. It confuses people, but that's what everybody uses. Okay, so unfortunately I have to use it. So this is the same thing as v minus 1 being in this epigraph, descent cone. Okay, so v minus 1 has got to be here. So now when you look at the cone, you think like there's like a whole bunch of vectors in there. If they're all subgradients, it's good and bad. Maybe we have a lot of subgradients. That's good to design algorithms. Maybe it's hard because then I have to go pick a good one. Okay. So one leaving out is one coordinate of that guy is fixed. So v minus 1 in the cone is not the same thing as just any vector in the cone. So you're saying the last coordinate of my vector has got to be -1. So usually how it looks like is like you take one coordinate and you say it's -1. Let's say last coordinate being -1. And you get like a compact cut of your cone. Because, imagine like an ice cream cone, you're just cutting it, saying the third coordinate has got to be 5. Yeah. So usually that's what happens, but not always. Because sometimes that cut just comes in like this, so you still end up getting like infinitely many. That can happen in kind of pathological cases, okay? At the end, this is what a subgradient is. We are gonna try to use these kind of stuff to replace the gradient, stochastic gradient descent type algorithms we have designed. The main problem is, now for a lot of functions, we don't have the derivative. We are trying to find a substitute for that, okay? All right, and what else we got? So if you pick a point inside your domain, what does that mean? Let's say your function is defined on like an interval. Inside is everything except these dots at the end, okay? Or if your function is defined on a 2D shape, stuff inside is what is interior. So it says if you pick the point in the interior, there's always subgradients. And moreover, in the interior, you get always like a compact collection of subgradients. And this third one I put as an exercise today. If you apply the definition in the case that the function was actually differentiable, then you get only one vector as a subgradient, which is the gradient vector. All right. Now, let's try to see what we can think in terms of directional derivatives. So we were doing Taylor expansion all the time in optimization. We got a function f, we say fx plus directional derivative in direction v, plus if you want to do one more, usually we don't. If you want to do one more, then you will have a Hessian, vector v transpose v times that Hessian, stuff like that, right? So, and then we use, gradient descent, stochastic gradient descent, just by looking at the first thing in the Taylor expansion. In the first thing, you will see the gradient multiplied with your vector v, which is the directional derivative. So let me write it up. So in the usual world, when we have derivatives, when we mean dvfx, we mean, take your gradient and multiply it with your vector v. And what does this represent? I'm perturbing my function in that direction v, and I'm seeing how much change is happening, right? And another way to write the exact same thing is like, if you write perturbation there minus your x divided by t, and if you take limit of t going to 0, you will get the derivative. However, that doesn't exist here. You don't take t going to 0 from two sides. You just take it from positive, okay? Because if you take two sides and if that limit exists, that means the thing is differentiable. Okay? That's a way to think about differentiation. But this makes sense for whatever function. You're just taking t going to 0 and trying to compute that limit. Okay? And in convex functions, this becomes much nicer than just some arbitrary function. Turns out this quantity is like very monotonic. It actually like decreases. When you hit 0, you get the infimum of all those differences. Turns out for convex, okay? So for convex, this becomes super nice. So this will be our substitute for the directional derivative. We'll just kind of look from one side, right? All right, and then you get your necessary condition, just like the usual gradient world, to have a minima. In any direction, you have to have this directional derivative non-zero, okay? In the usual world, this will be any direction equal to 0. Because directional derivative will be gradient times vector v. And to get the minima, you have to have gradient 0. So in the usual world, when we have differentiability, local minima means you have to have all the directional derivatives just vanishing, okay? Here we cannot just say vanishing, but we are able to say they gotta be positive or 0. That means anywhere you go, your function is increasing. So like a local minima, okay? So it gives you the same type of criterion where you replace usual directional derivatives with this one. Okay, that's the first thing. Now, so this is actually not so hard to prove, but let's not worry about it. Okay. And as I said, there is a little more to the story. Probably I'll put this as an exercise today. Like if you pick a number and look at that difference, and if you pick a bigger number and look at that difference, turns out it's like increasing as the number increases for any convex function f. Okay. Before you work through this, this is kind of like, come on, this should be a lie. But when you work through it, you realize actually it works. Okay. So this I'll put as an exercise. So, but knowing that, you know this expression is get the smallest as this number getting to the 0. So literally the limit from the going to 0 from right we were talking about is the same thing as if I would just take the infima, because it's always decreasing. Okay. It's super monotonic, super nice. All right. Basically what you do, look at the difference. I'm perturbing my function in the direction of v. And I'm dividing, let's say I perturb like, this is, think about it like a step size. And divide it by your step size, you get a number here. And think about what is the smallest number you could get if you're allowed to mess with that t. That ends up the directional derivative in this world. Okay. All right. So that's the first thing. Second thing is like, this thing has a lot of nice properties. Like if I got two functions and do this, it's the same thing as I do it separately and I sum it up. If I have like a vector multiplied with a number, you can just take it out. So even though this thing is like not necessarily a linear operation, it behaves almost like linear. So it's quite nice. Okay. And then I don't know if I'll put it as an exercise when I was writing notes. Probably that's what I thought, but I'm not sure. So there's even something nicer. Like if you take two vectors and combine them, you know, think about when we discussed this coordinate descent, right? It was only looking at coordinate directions, right? And suppose you don't only look at coordinates, you say combine two coordinates, look at their combination. Can you perturb in that direction and maybe decrease your function? So for that kind of questions, turns out directional derivative in a combination, in this sense, when I say directional derivative, it's not really a derivative, as you realize. So it works out in the nicest way you could imagine, basically. Okay. Yes, question? Yeah, that's what he was asking me. Like when we were discussing coordinate descent, like if I knew the correct direction to go, I was able to decrease more for some examples. So we went through under which assumptions coordinate descent actually gives you the best option. So we can refer back to the recorded camps. Yes, exactly. All right. So now, what else we got? So if you do some math, this also gives you another description of the subgradient vectors. For a vector to be a subgradient, turns out, just take that vector, multiply it with your direction v. That number you get should be always less than the directional derivatives we talked about. Okay, and this should hold for any direction. So a different characterization of those subgradient vectors. So let's try to pull back our intuition from the differentiable world. In the differentiable world, this is an equivalent. Okay, if u is replaced with the gradient vector of your function f, gradient times v equal to directional derivative in the differentiable world. This u is now trying to behave like that gradient. It's a subgradient. Okay, so for any v you pick, it gives you a number less than equal to the directional derivative. Okay. So that's another characterization of the subgradient vectors. All right, and we can say even more than that. So I know now for every subgradient vector u I picked, this number is less than equal to the directional derivative. Okay, and now suppose I'm going to try to go find like the biggest u, in the sense that I picked a v, and I'm looking for all the subgradients and computing this number. Let's see what is the biggest I could get out of it. Okay, and turns out this actually then becomes equal to that directional derivative. Okay, they are all less than equal to this number. And if you take the suprema, you get the equality. So directional derivative, you can also see it as think about all your subgradients, multiply them with your direction v, look at the biggest number you get, that turns out to be a directional derivative. But this is kind of like strange in the sense that we get to directional derivative as an infima before. Now the same thing shows up as a suprema. So it's like a tiebreaker between two roles, turns out. Okay, so how did we get to that as an infima? We were saying I take my f, I'm at x, okay, let me perturb it in v direction, t much, fx plus tv minus fx divided by t. Let me go back to there. So this was the other characterization. I'm going in that direction. How much change happened? Divide by. Look at all these changes. The smallest one was giving you the directional derivative. Okay. Now, if I look at the same guy from the side, okay, you get your direction v, and you're multiplying it with u. And if u is going through all the subgradients, turns out you get back this dvfx. So in this world, this guy is like infima. In that world, it's like a suprema. So it's like the tiebreaker between the two quantities, looks like. Okay. All right. And this will be useful, of course. Yes, go ahead. So gradient, very good question. So the question is like, I am at a point X and I'm going to go in some direction and I want to say most amount of decrease in my function. Where do I go, right? And the answer is minus gradient. Minus gradient is like the steepest descent. And we talked about this in class, and also you guys have an exercise probably just doing that on canvas. Likely, I have to check. My memory is not great, but I think I put it as an exercise. So the answer is minus gradient is the steepest descent direction. Now, the analogy here is like, I am thinking all these guys, subgradients, when I take minus of them, they might behave like minus of the gradient. But since I have a lot of them, I need to think about which ones are actually behaving like minus subgradient. Okay, very good question. Okay, so this is so far what we got about this stuff. Good question. Do I want to talk about how the prove this suprema is actually achieved or not? I would like to talk about it, but probably I shouldn't. So I'm skipping over the proof. I think there is a very nice idea here, but would knowing that give you a lot of insights? Not sure. So let me not do it now. Of course, these lecture notes will be available. If anybody is interested in checking why this is true, happy to discuss anytime. Okay. I'll not give you the proof for the sake of using our lecture time better. So this is the result we're using. Okay, very good. Now let's do a summary of what we did so far. Okay. So subgradient is the type of vector. When you do x plus b minus x, u times v will be always less than that difference. That kind of u is the subgradient. That was the first definition we got. Then this is the set of all subgradients denoted with this funky notation. And then we noticed being a subgradient for a vector is the same thing as v minus 1. That vector and last coordinate stack up a minus 1. That's got to be in that descent cone. And then we define directional derivatives, taking the limit only from one side. And it turns out this function, this guy right here, even though it looks complicated, it apparently behaves nice when your function f is convex. It's literally an increasing function. So this gives us another way of looking at the directional derivative. It's literally infima over all these temporal differences. And directional derivative kind of delivers its promise in the sense that it gives me a criterion to check optimality. If I am at a local min, then the directional derivative has got to be non-negative. And the last thing we discussed was this directional derivative also gives another way to look at the subgradients, which is take your directional derivative at a point in the direction v. That's a number. And if you take a vector u dot product with that direction V, the number you get is got to be less than this number, okay? And subgradient satisfies it for any direction V you could think of. So if you're a vector satisfying this inequality for every V, then you're a subgradient, okay? This is another characterization of subgradients. And actually the biggest one, when you push it to the limit, when you fix a V and look at all subgradients and pick the biggest number you could create out of this dot product, you literally end up recovering the directional derivative. The suprema actually touches, right? So this inequality could have been correct, but there might have been a gap between what subgradients can do and what this guy is. There's apparently not a gap. You pick the greatest number giving subgradient, you end up recovering this one. Yeah. Right. And in the differentiable world, of course, you only get one subgradient, which is the gradient vector. And when you plug in gradient vector here, you get an equality. Okay. Right. Very good. So that's the direction. So what do we want to do with all this stuff we discussed? We would like to find a descent direction. We want a direction V where the directional derivative is negative. In other words, for sure, whenever I take a subgradient, u dot V is going to be negative. And ideally, we would like the steepest descent, right? So in the sense that think about all the directions with unit norm, pick the one that gives you the most decrease since we are trying to minimize a function. That's ideally what I would like to do if I can. I don't know, we'll see, okay? So, but as a bare minimum, I want to find the direction. If I go in that direction, the directional derivative is negative, I'm like decreasing my function. That's the bare minimum for like our wish list, okay? All right, and in our earlier discussion, that descent direction V was given by negative of the gradient vector, usually, or a sampled version of it if you're doing stochastic gradient descent. Okay, very good. Now let's look at maybe an example before I do more stuff, or should give me a sec to decide. No. Yeah, let me show you an algorithm and circle back. Because if I talk too much without talking about an algorithm, I start feeling kind of guilty and itchy. So let's talk about an algorithm. Okay, to motivate the algorithm, let's look at an example first, then we will talk about the algorithm. Okay, so here, what do we see is a function f that is defined like this. Let me write it up here. Fx is maximum among a1 times x, a2 times x. Let me maybe take this guy a little up. Sorry, it didn't work out so nicely, so let me write it again. So I got two linear functions. And I'm taking maxima of them. You know, you put your x, you dot product with two vectors, and you see which one is bigger, you pick that. That's what this function is, okay? So when you plot it, this is level sets of this A1 vector. Suppose these are the x, A1 times x is 5, A1 times x is 3, something like that. This is for A2. A2 times x is 3, A2 times x is 5, etc. When you think about this function, if the thing on this part is bigger, it picks that. If the thing on this side is bigger, it picks that one. But they can be also equal. Then you could pick any of them. The equal case is like these corners, where both A1 and A2 gives you the same output, okay? Now, suppose you're one of those corners, like you're at this x. A1 and A2 are equal, okay? So this is an example by the book of Recht and Wright. I think I put links to that book. I'll give you again. So if you want, you can take a look. I need to cite since I'm using their example. So now they're looking at a point x where both maximum, like the two things are equal to each other, okay? And then what's the subgradient direction? Well, turns out either A1 or A2 or a convex combination of them serves as a subgradient direction in this case. turns out, okay? So the subgradients, if you plot all of them, you literally get this like line segment looking thing. You're starting from a dot A1, A2, and like, drawing things in between. So all of these guys apparently is a subgradient. But when you look at the plot, you see some of them is not gonna decrease your function. If you go this way, in this guy's direction, the function increases, okay? But if you go this way, it seems like it's decreasing. So not every subgradient works as we like it to work, basically. So we need to pick carefully if we manage. If not, we have to do some tricks to make it work. That's the main punchline here. So subgradients is a collection of vectors. Some of them works like what we want them to do. You go in that direction, your function decreases. But like, let's say, pick this subgradient, go in that direction. Well, it's bigger than the level set of x. So your function increases, basically. Okay. So my point in this example is not to confuse you, just to tell you that you need to think about it before just picking a random subgradient and we're going in that direction. Yes, Adam, you have a question. I can't tell. Tell me the question if it is okay. I think you maybe missed some of it when you were out. So the function is no problem. So you got A1 and A2, two vectors. You in dot product it with your x, and it gives you two numbers, pick the big one. That's the function. And then these are the level sets of this A1. These are, say, x, A1 times x is 5, A1 times x is 10, blah, blah, blah. And this is the A2. And sometimes they coincide. For this guy, both A1 and A2 gives you the same number. And take such an x, all this line segment comes out as a subgradient. You have to check that's the case. But if you pick a random subgradient, and if you go in that direction, you may not get your function decreasing. Sometimes it increases. Only the guys here, for example, are decreasing this much. Okay. Gray is the part where you go less than what you had. So gray is decreasing direction. So this was like, say, fx equals to something. If you go in this gray direction, you're doing what you want to do. This is all subgradients right here. And if you pick from x and go in any direction, so the dotted line is the beginning and the end, you could go in any direction here. But some of them doesn't do what you want to do. Okay, pretty good. Okay, now so there are two ways to go about this. I'll give you first the practical one and the second more theoretical one. So the practical one says the following. This is called subgradient method. Okay. And you need an assumption in how big are your subgradient vectors you picked. That's the only assumption you need, more or less. So at every step, this algorithm will pick a subgradient blindly. Some of them may be increasing, some of them may be decreasing. The only condition you put on, you say, these subgradients, they should have norm less than a number you picked. Don't go pick a big subgradient, okay? That's the only thing you're imposing. Then the trick to make this thing work at all is you create a weighted combination of the places you went to, okay? That's what the algorithm does. Okay, let me tell you how this goes. So you decide on a number of steps, say t, 10, 100, whatever. Think about this whole thing as your one iteration, okay? How does that go? So at every step from 1 to t, the algorithm picks a subgradient vector, and then you pick a step size and you iterate, just like our gradient is, okay? But the problem is we don't know if it's actually descending or not. Some of them may be increasing the thing, since we just pick them blindly, okay? And then there are some things that still hold. One is if this guy is a subgradient, by definition, if I dot product it in the direction I iterated, it's got to be less than this change. That's the definition of subgradient. That works still. And the second thing that works is like usual linear algebra is still true, okay? And when you combine these two and you start analyzing what does this thing do, you get something like this. So what you're going to do is like, you're not able to prove that if I iterate, I get to something good. What you're able to prove is the following. I iterated through, that's why I put like a bar on them. That's not what you're going to end up using eventually. This is going to be part of the iteration. But what you will use is just, you will take their combination. So I put step sizes at every iteration, right? So multiply your vector, the place you are at, with that number, sum it up, and divide by summation of those numbers. Okay? I'm like taking an average of what I have seen so far, basically. That's literally what I'm doing. It's a weighted average, though. Weights are coming by the step sizes you picked. Okay? And then for that guy, you're able to prove the difference from that to that is like some algebraic expression, which I'll go through, and I'll give you a nicer version in a sec. But the main interesting thing here is like, you do all these subgradient iterations, you don't really know what's going on, but somehow when you average them over, it starts behaving nice. It almost behaves like stochastic gradient descent. For some reason, if you do those step sizes correctly, right? And then what you end up getting is like, you do this algebra right here, you put that G, blah, 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 you get something of this sort. What does that mean? Well, this difference is less than equal to some number divided by this summation of step sizes plus squares of those step sizes, biggest norm your subgradients could take divided by that sum again. And I want this thing to be small, okay? Suppose I did like T steps and I took the average one, and I would like average to be getting close to the optimal. So how could this thing be small? Well, first off, this number shouldn't be too big, which means the place you started the iteration should not be too far away, okay? Second, I want this summation of step sizes to be a big number, so that when I divide this guy with that, I should get a small number. So I want this sum of step sizes to be big. However, there is a trade-off. There is also squares of step sizes. Okay, I don't want that to be big. Okay. So at the end, I have to pick step sizes so that their sum should be a big number. Some of their squares should be a small number. Okay. It's kind of weird. Okay, so how do you pick a collection of numbers? When you sum them up, you get a big number. When you square them and sum them up, when you expect something bigger, you should get a very small number. Okay, so there are many ways you could do this. One way is pick them as 1 over root t, for example. Okay, when you square them, you're summing 1 over t, and it gives you something like logarithm. When you don't square them, when you just sum them up, you're summing this. Everything here is at least 1 over root t, because you start with like 1 over 1, 1 over root 2, 1 over root 3. The smallest guy is this. So the entire sum is, of course, smallest times the number of things. It's square root of t. So the sum comes out as square root of t. If you pick this step size, you can pick other things too. Okay. And the sum of squares comes out to be a log t. So the bound you end up getting looks like this. The difference from where I am at by this averaging blind subgradient descent is how far off I could be when I started the bound on the subgradient vectors I picked, logarithm divided by root t. So I would like a t or t squared here, ideally. But the fact that I can prove anything at all is interesting, because I'm just picking subgradients very blindly. Some of them are increasing, some of them are decreasing. But when you average them over, somehow the increasing ones get canceled out and you get some improvement on average. That's why it sounds like stochastic gradients. I'm just averaging over kind of randomly because I don't know what are those subgradient vectors I picked. But still, you can at least do this if you can do nothing else. Okay, so you just pick whatever subgradient, find a cheap way to pick a subgradient depending on your problem. Keep iterating, cook up the step sizes. You'll do some improvement. Okay. So that's one thing you could do. You might say, okay, this is just like trying to be too lazy. I want to work harder. I want to find a good subgradient where I know it's actually descending always, or like descending a lot, something like that. If you go through that route, usually you end up in some place like this proposition. What is this saying? Look at all your subgradients and pick the one that has the smallest norm among them. You got like a collection of them. Okay. It's like a compact set. Pick the one, the smallest one, that has the smallest norm among all the subgradients. And turns out that guy is guaranteed to be a descent direction. And actually, it's like the steepest descent analogy here. Okay, so how do you find the analog of minus gradient vector? Turns out go pick the subgradient, which has the smallest norm, minus it. You get your best direction possible. But of course, how are you going to do this computationally? Okay, that's the main problem. So you can prove this, but like, how do I go find that smallest one? So if your problem is nice enough and you can approximate this quickly, you can run this scheme also. Instead of picking blindly whatever subgradient interaction, you can pick a good one. Even if it is not the minimal, that's okay. You pick as small as you can. You could do like a line, what is it, backtracking type thing. Pick a subgradient if you're able to pick it quickly. Good. Pick another one, see which one is smaller, keep iterating, something like that. So if you're able to execute something of that sort in your problem, then you can also do something that looks more like gradient descent rather than stochastic gradient descent. Pick the smallest subgradient, minus it, go in that direction. And you can even use like constant step size and stuff. Yes, go ahead. More like how the function is behaving. Like if it is like too far away from being differentiable, imagine like a sharp corner in the function plot. That kind of stuff gives you a lot of subgradients. Yeah, but then you just pick one at least and keep going. So as the more your function gets closer to being differentiable locally, the less subgradients you will have. And functions sometimes, it might be differentiable in some parts of your domain, not differentiable in others. Sometimes maybe you're in luck, you already have a gradient vector, just one subgradient, good luck. Yeah. So yeah. So it's more like how far away from your thing being differentiable. Okay, so far so good. Any questions about this? The analogy to steepest descent. So minus of this guy is the minus of gradient analogy, basically. Pick the smallest norm, subgradient vector, minus it. How do you do that, or can you approximate it quickly? Will depend on your domain and problem. Okay. All right, very good. Now, before I say more, let me remind you why do you even care about this? This kind of stuff is actually what you see most of the time. You will have a loss function. You'll put it on a whole bunch of your data, right? Compare it against your label. This is the parameters you're optimizing over. This is your loss. And it's empirical loss, right? That's how we do. We do like batch and whatever we're doing. So put the data into your loss, sum it up. This, depending on how it is, it may be differentiable or maybe not. Suppose this is differentiable. You have a nice loss function. But then we start regularizing usually, right? So next to it, we put a regularizer on the parameters we are picking. We put an L1 norm, L2 norm, I don't know, entropy, whatever we are putting there to regularize. And a lot of those regularizers are just convex. They are not necessarily differentiable. L1 norm is a good example. And we want to work on those type of things too, of course. So then you cannot just say I'm doing gradient descent because there's no grade sometimes. Okay. So it's motivated basically by practical needs. So I'm not saying people are always careful enough to use this kind of algorithms when you need to use. Sometimes people still would run gradient descent and maybe it's still okay because your function is almost differentiable. You get, it works out, but this is what you're supposed to do if you really want to do it seriously. Okay, now let me get back to finishing the other discussion I skipped over. So we talked about subgradients. I show you the subgradient descent algorithm, which is picking blindly and averaging over. I talked about the optimal subgradient interaction. And let me tell you a little more structural results. Then I will circle back to more algorithms, okay? Okay, so far let me take a little pause. Yeah, we did some structural stuff and we saw an algorithm. Now we will do a little more structural stuff and we will see another algorithm. And I may or may not get to finishing that algorithm today. We'll finish it for sure next time. And next lecture will be last optimization lecture. But that's going to happen next Tuesday. This Thursday, we have an industry speaker on Zoom. Okay, I'll tell you more details when we finish the class, also right on Canvas. So this Thursday, you don't have to come to class. It's on Zoom. We have an industry speaker. Next Tuesday will be our last optimization class. Then we'll switch over to randomized techniques. Okay. Probabilistic techniques like streaming, sketching, hash functions, dimensionality reduction using probability, stuff like that. Yeah. And maybe also one lecture on Markov chain Monte Carlo. Right. Okay. Now let's get back to our structural discussion. Suppose I got a summation of two functions. One of them is differentiable. The other one is convex. Okay. The convex guy, think about it like your regularizer. Differentiable is whatever loss you're working with. And sometimes that loss function is convex as well, sometimes not. But usually differentiable. Okay. Okay. Now I want to know if I try to optimize this guy, what are the criterions for me? Right. Can I do a little better than what we saw so far? So far, what we have seen, if you're at a local minima, all your directional derivatives in this world are non-negative. They're zero or bigger. But here I have a little more structure. Now I have a differentiable part and I have a convex part. And this is very common. This is a typical situation. So can I say a little more when I have that structure rather than just talking about the F, which was convex or not? Okay. Now, what we know in this situation is recorded here. If your first part, the differentiable part, is also convex, then there is a if and only if necessary and sufficient criterion. Okay. If your first guy F, so let me remind, first piece F is the differentiable piece. Second piece C, I guess, that Greek letter, is the convex piece. But the differentiable piece sometimes could be also convex. Let's say if you're doing least squares loss, what is called MSE, minimum squared error. But if you're doing usually like cross entropy, a lot of those stuff is differentiable and convex. Cross entropy may not be differentiable if you're doing on discrete, whatever. Okay. So convex and differentiable F and a convex regularizer to C. Then we know for sure, if and only if, being in a min is the same thing as you can write 0, 0, 0 vectors as gradient of the differentiable guy plus a subgradient. Okay. In the usual world, what was the analogy? Gradient is got to be 0 when I have convex and differentiable. Now you have a gradient for the first piece, but the second piece does not have a gradient. It's not differentiable. So you're allowed to pick any subgradient. And if you could create, now the summation is like looking like the gradient of the whole thing. If you can hit 0 by adding a subgradient to that gradient vector, then, okay. And the second thing, if it is even nicer, if you are strongly convex, you have the first thing on top, the minimizer is unique. It's almost like your usual, because now, yeah, okay, anyway. So this is like super nice situation that doesn't always happen. And the last one is, it's just differentiable, not convex. Then you're able to say, this is a necessary condition. 0 vector I should be able to write it as the gradient of the differentiable part plus a subgradient. This, you have to have it, but it's not sufficient anymore since this is only differentiable. Yeah. So this is the structural results we have in this world. Very good. Now I'll build up to something called proximal point method. This thing existed maybe for 40 years now. I don't know, maybe longer. Still, variants of that idea is what you would use if you're doing non-smooth convex optimization. So this is what I'm going to build up to now, which you will have to bear with me with 5-10 minutes of technicality. Initially done by some person called Rockefeller. I don't know if Papa was one of those rich Rockefellers or not. So he is like one of the big names in convex optimization. And if you really want to learn this stuff, this person's book is like the reference. If you just look convex analysis, Rockefeller, that's like the book. If you know it by heart, you know all this stuff really well. Okay. And Rockefeller came up back in the day with this idea called proximal point method. And I'll build up to that and tell you what that is. And there is variations. Of course, after the first invention, there is improvements. We'll talk about those too. Okay. All right, now to build the proximal point method, let me first define a useless function, which will become useful soon. The useless function goes like this. Suppose I have a set omega, which is convex, and I have a barrier function, which goes like this. If I'm outside of the domain, I get infinity. If I am inside, I get 0. Okay. If your set is convex, turns out this function also comes out as a convex function. And being convex, you can define like subgradients and whatnot. And apparently, when you do subgradients of this function, you get back those descent cones and a lot of nice properties. But, computing with such a function is usually not fun. So it's useful more conceptually. So let me try to explain. Suppose I am trying to optimize some stuff on this domain, and I'm going to use a projected gradient type method that we discussed. What was that doing? You have a point X. You go project it to the closest thing on your domain. You iterate. You do that again. That was the projected gradient descent algorithm. Okay. I want to do projection. So how do I express projection? Well, at every point X, the projection guy is the closest inside your domain, right? So look at the distance to your domain, minimize it. Argmin will give you the projection. Well, instead of writing the domain here, you could get rid of it and just write that funky function. What does that function? What was it doing? It's infinity if you're out, 0 if you're in. It's basically imposing this condition, right? So these are equivalent. But for now, it's just like an abstract nonsense thingy here, okay? But this gives intuition to build up this proximal point method, which is maybe I'm not able to come up with this function, but I come up with another function, which is easier to compute with, but it still captures my domain somehow, okay? Let's say I'm trying to find a best probability assignment among 10 classes of objects. What are the options? You're going to have a vector with 10 coordinates, and every coordinate will represent the probability of that class, right? First class, 1 out of 10, second class, 1 out of 5, whatever. What are all such assignments? All vectors with 10 coordinates where they sum up to 1. Yeah. That gives you a domain. You can try to write very explicitly like this, or you try to come up with a nicer function approximating that domain. Instead of getting the equality here, replace this with a nicer and easier function so that you can run this optimization quicker. And what you get will be an approximation to what you want it to do. Okay? That's the idea behind this proximal point method. Let me give you examples. Or let me define it first, and I'll give you examples. Yes, right here. So what you would like is you will get a nice convex function for yourself, which somehow captures your domain. There you need to use some intuition to design a function, okay? Then instead of that, crazy guy going between 0 and infinity, you will use this nice h. You will say my hu. This is a proxy for checking if u is in your domain or not, okay? This should be a function. As you get away from your domain, it gives you big numbers. If you're in, it gives you small numbers, okay? And then what you do, your projection now is I'm at a point X. I minimize my convex plus super nice distance, Euclidean distance function. And at every step, I'm going to try to run this optimization. Since I'm going to run it every single step, I want it to be quick, basically. Okay. All right. That's this projection operation is what gives that proximal point algorithms, which we're about to talk about. One quick thing you could prove, this projection is actually decreasing distances between vectors. So it behaves as you kind of like it to behave. Okay. Suppose, what's your intuition for projection? I have two vectors in 3D. I project them down. They can get closer, but they cannot get farther apart. Think about two stuff here and look at their shadows. What's the distance between two stuff here in 3D versus distance between their shadows on the plane? You would expect it to maybe the same, but maybe smaller. You could get like 2 points projected down to exact same thing, right? Let's take two dots, right? They have a distance, but when you project, no distance at all. So that's what you would expect from a projection. If you defined it right, it should not increase distances between stuff, it should decrease them. And this works out exactly like that. So here's an example, our L1 norm. So let's try to work out this idea on L1 norm and see how it comes about, okay? So in L1 norm, the projection, if I use that L1 norm with a lambda parameter as my convex function, the definition will look like this. Okay, very good. And now let me write it down in detail. What is the L1 norm? Absolute values and sum up those stuff. That's the L1 norm. And here is that lambda. And I just wrote down the Euclidean distance. And if I am a point X to find the projection, I'm going to try to minimize this. I want to find the U vector, which minimizes this quantity. But when you look at it, you realize it's very coordinatized. Actually, you can just go by one. Find the best U1, find the best U2, because U1 coordinate only talks to X1. So it's very coordinatized. So it becomes like a univariate optimization question now. Every coordinate, put the best thing there. Okay? And then basically, I can go just look at one coordinate and understand the whole thing. All right? And then if I write it down, this X1 minus U1 squared, the Euclidean norm is here. Lambda times absolute value of U1 is here. So I'm in a kind of good spot. I have only one variable, which is U1. X1 is given, that's your point X. And I'm going to try to optimize it. So if there wouldn't be an absolute value, I would just take derivative, put it to 0, that will give me the optimal U. I'll do my calculus. I just have one variable, and the thing is quadratic, super simple. We know how to solve this right away. You don't even need to run any algorithm. We have a closed form solution. But the issue is this guy is messing up, okay? So we got the absolute value. I don't know what that is. So let's split the problem into two pieces, where first piece, you're looking at the positive type stuff. And in that case, absolute value becomes just U1. And you write it down, you take your derivatives, and comes about as the optimal choice here is apparently 2 times the first coordinate minus that lambda parameter divided by 2. And don't forget, we are looking at the positive type assignment here. This means this is a positive number. And that apparently also means your first coordinate is bigger than half of your penalization parameter. If this is the case, this is the optimum. Okay. And then you look at the negative one, you do the same story, do your calculus, find the optimal closed form. And if you're looking at a negative assignment for the first coordinate, apparently it comes about as follows. 2 times your first coordinate, x1, times your penalization lambda divided by 2. And this has got to be negative now, which means your first coordinate was supposed to be less than minus lambda over 2. And the third option is your U1 is neither negative nor positive, it's just 0. That's the third option. Let me summarize what you get out of this with a picture. It looks like this. You look at your vector x, you go coordinate by coordinate. You look at the first coordinate. And if the first coordinate is less than minus lambda over 2, your optimal assignment is this guy. If your first coordinate is bigger than lambda over 2, Your optimal assignment is this guy. And if it is something in between, you just put 0. Okay. So it's like, they call it soft thresholding. You get to pick your threshold lambda. It's up to you to design that. And then what this does is like, it just imposes lambda over 2 thresholds. If it is less than lambda over 2 or less than minus lambda over 2 here, just push it to 0. If it is bigger, it does this operation on them. Okay. So that's how this operation comes about if you work it out in the L1 norm case. That is one of the most common things that you would use in this type of stepping. Okay. Any questions so far? This is going to be our this projection operation with any function h will be our building block for the algorithms that you're about to see. Any questions? Okay, so L1 norm, is a good proxy for the simplex, for example, I was talking about, right? You just need to think about the shape you're trying to optimize over, come up with a function h that somehow gets close to that shape. Okay. All right, now let's get to proximal point type algorithms. Very good. Okay, so let me see what I want to show you first. Okay, so this is the oldest proximal point algorithm where you got no structure whatsoever. You only have this is this Rockefeller proximal point method. This is convex analysis is the book for this field. And this is what Rockefeller came up with many years ago, maybe 4 or 5 decades ago. I have to check the exact date. And this is the situation where you got no structure, no differentiability. You only got a convex function. And you want to optimize this guy over the entire Rn. What would you do? Well, what you do is this. You say, I'm going to regularize my convex function with Euclidean. And when I put Euclidean next to it, since this is like a super nice function, strongly convex, differentiable, everything. This regularization makes the optimization question nicer, okay? A priori, when you look at it, the problem I started off with versus what I'm writing here, this looks more complicated. But because of the effect of this function, the optimization question gets nicer and easier, okay? And in a way, you could say Rockefeller had the regularization idea we use in machine learning now, maybe 5 decades ago, because he was regularizing this convex unwieldy function with Altoona. So, and then what is the algorithm? Well, you literally take that regularization and define your projection using your convex function plus this one, just like the projection we were doing. The H was something you're going to design to represent your domain. Here you got no domain, just the entire Rn. Just use your convex function you're trying to optimize over. And you define that projected gradient descent, where the projection is, do a iteration and then project it back. Literally, this is your xk plus 1. Okay. So you're at an xk, do this. That's your next step. Or with the language we wrote down, the same thing can be written like this. Projection using alpha k times your function phi. Okay. You might say where this thing came from. It came because I was dividing here with alpha k. In the usual one we did, there was no division. There was nothing. Okay. There's just some tricky stuff people always do. At the end of the day, you can prove this gets closer and closer to the optimal. And the convergence rate is linear with number of steps. So the only bottleneck here is how quick you can do this part. So this is like when you have no structure whatsoever. You have a convex function, that's it, you want to minimize it. Okay, that's what this person was doing many decades ago. And the computational bottleneck is this iteration step. If you're able to do this quickly, then you can run this quickly. If not, it's not going to run quickly, but that means it was a hard problem already. You just made it at least nicer for us. Okay. Now, what are the variations of this? The variations we will see will be similar to what we have seen so far with this projection idea. Okay. We will see proximal gradient. We will see proximal coordinate descent. So what we have seen gradient descent, stochastic gradient descent, coordinate descent, right? So now people develop all that stuff in this world. Basically, that's what's going to happen. All right. So, all right. And as I said, I don't think I'll finish all of this today, but we're almost done. Okay. So what did I show you so far? I showed you what is that projection. It's like the proximal point. You get to the closest point in the domain, or like closest point in your projection. And we show Rockefeller's old algorithm. Now we will see the same idea, trying to do gradient descent and coordinate descent, and that will be it. Okay. I have my function fx plus lambda times cx. C is the regularizer. I got the lambda regularization parameter there. F, for now, assume it's both differentiable and convex, this guy. Okay. And what do? You define your convex function h, take the iteration, distance from your u, plus the regularizer part. And finding the u that minimizes this thing will be the projection step. I'm trying to do something like projected gradient descent. I do the gradient, then I go find the u that looks like that gradient, the closest u I could get, basically. Okay. All right. And that's basically the algorithm. This is what's called proximal gradient descent. Okay. And the proximal is coming from this projection type step. Okay. And for this general family of functions where your f is differentiable and convex and the c is just convex, you're able to prove this thing actually converges. And moreover, if you know about your convex function, some Lipschitz type bounds that we were using, you get a bound that looks exactly like the gradient descent bounds we derived. But this time we have a function that is not necessarily differentiable. Let me go through it once again slowly. So this is my objective function. This is the nice loss function part, convex and differentiable, suppose. This is the regularizer, which is not necessarily differentiable. It could be L1 norm, whatever else you like. Log loss, cross entropy. Okay. And then I want to optimize this guy. I want to find the parameters best fitting this one. And then what do? You imitate the gradient descent with this proximal idea of Rockefeller, or this projection idea. What is it? This is your regularization part. This would be how your gradient descent would be looking like if you would be having just f, right? But we do have also this guy. So we try to approximate that situation by finding the u that is close to that gradient, but also not making anything here like go crazy. Now I doubt why I don't see that u right there. I'll check if I did any mistake here, probably not. And then that's how you run. You find that u, you keep iterating, and you end up proving almost exactly the same result we had for the differentiable case before. Yeah. And this is the estimate right here. Okay. Now the coordinate descent version of this. Well, maybe I can actually finish it today. That means probably I went very quick, sorry. Now, when we got the gradient descent, the next standard, instinct is like, can I also do this coordinate descent type thing, which was easier to implement. Just mess with one coordinate every step. And you can do it in the situations where the regularization part is like separated already. You remember we had this graph type problems where one part was involving the edges between the nodes, and the other part was only putting some weight on the nodes. This is one way you could see this kind of stuff, but not the only way. So what you need, for example, this could be L1 norm, right? X1 absolutely, X2 absolutely, that works. What you need to make this work is you got your, convex, differentiable, whatnot part, plus the other part, which is only convex, may not be differentiable, should be separated coordinate by coordinate. Okay, and then we can do coordinate descent. How that's gonna go? You pick one of those coordinates randomly. All the coordinates that are not picked remains the same in one step of the iteration. And the coordinate that we are gonna update is going to be updated using this proximal or projection idea. What we are gonna do what you would do with only the F without that G convex but not differentiable stuff. Then do the projection using that one G that is relevant to the coordinate you're talking about. So let's think about this slowly. So what am I doing is I am picking my coordinate randomly and look at the objective function, the G part here, the convex but not differentiable part. Come on. Yeah, right here. Only one of them, one of those GIs, is relevant to the coordinate you picked because it's like coordinate by coordinate. So now what you do, you pick the coordinate, just pick that G, just only one. Okay, and then this guy is differentiable. Just look at the partial derivative corresponding to the coordinate you picked. Just one coordinate of the gradient of this guy. And that's all you need to do that coordinate descent update. Okay, so what we will do the gradient of the F, and we will do the projection using that particular G that was talking to your coordinate. Basically, an simplest version of that Rockefeller idea you could think of. You have just one variable, one coordinate, one function G, and one partial derivative. Okay. And you can even just write this down. And the thing you will pick, apparently the solution to this, comes out as the minimum T of this quadratic function. And we are able to optimize quadratics very quickly. So basically, every iteration is quick to compute. Okay, and what kind of guarantees we can prove for this? Well, let me show you the case where you got the nice type of function, and that's good enough. If your convex part was, strongly convex, differentiable, that F part is super nice. And this GI regularizers are just convex. And my objective function is a summation of that nice F and the convex regularizers. And I'm running this projected coordinate descent, coordinate by coordinate, as we described. And I'm picking a random coordinate at every step. Then it comes out like the error when you started. And at every step, so what are these M and N? So at every M is the strongly convex assumption of your F. N is the number of coordinates. So M is a constant coming from your function F. Okay. So what are you seeing here? 1 minus a number raised to the power K if I did K iterations. It's very good bound actually. Okay. But it's in the case where your F is super nice. Okay? If it is not super nice, you can still prove some guarantees. It almost looks like the usual coordinate descent guarantees actually. So the punchline is, if you have this kind of situation where the regularizer is coordinatized, like L1 norm, like here, then even if things are not differentiable, you can do this projected or proximal gradient descent. And it works as if you would have the gradient descent as well. Okay. All right, let me see if I want to say anything else. I think, yeah, this is like, this is all I think I needed to say about non-smooth optimization. The only remaining lecture is about duality. So in optimization, there is a very, of course, I'll not start it now. I have like 2 minutes, but I can just tell you a little bit what you're going to see. So we have a lot of computer science majors here. Have you heard of something called like max flow equals min cut? You don't have to be a CS major to hear this. Well, what's that? You have like a graph, and you want to send the flow through, say, a source to a sink, okay? And you get to pick how much flow you're sending. Let me draw something to make this more reasonable. Okay. So suppose I got like a graph, you know, it's got a whole bunch of edges. It's a complicated network. And suppose this is the source, this is the destination. And now I would like to find the flows that I need to send, literally numbers, so that I could transfer them through the network and they will arrive to the destination. And every edge has a capacity. Think about it like a pipe you're literally pushing a flow through. Okay? And then you want to find the maximum flow you could do. That's called max flow problem. Okay? And then another problem, so this is max flow problem. And here's another problem that's called min cut. What does that mean? A cut is literally you get a cut. Let's say I'm cutting through here. Then I look at which edges I cut through. And I sum up the weights of those edges. Okay. And I try to minimize, sum up the capacities of those pipes. Say. And I'm trying to minimize the cut. Okay. But a cut means after I do the cut, the graph becomes disconnected. It's not connected anymore, so it's cutting. Okay. But I want to do the minimum damage. What is the minimal number I could get? Turns out these two questions give you the same answer. Okay. As optimization problems, they're equivalent. If you solve one of them, you solve the other, turns out. So the theorem that I was trying to mention says max flow equals min cut, which we probably will touch base in next lecture. But this is just an instance of a more general fact from optimization. In optimization in general, in convex optimization, in particular in a stronger way, when you have an optimal optimization question that you're dealing with, there will be always a soulmate of it, okay? There will be always a dual problem. Another optimization problem, which may or may not look so similar to each other, but they will give you more or less the same answer. That's the duality idea. If they give you the same answer, we say there is no duality gap at all. They just are equal like this situation. This is, in particular, linear programming duality. So you can phrase both of these problems using just like a linear optimization. And then in linear optimization, there is no duality gap whatsoever. Then you say, just by duality, I know max flow actually equals to min cut. I don't need to prove it. But in general, you will have an optimization problem, and I'll tell you how you create the dual one. And the dual one will always give you a lower bound for the primal one. Okay? It will always say your primal is bigger than blah. But if you have the guarantees that they're equal, it will also tell you your primal is actually blah. So that's what's going to come out. And when you learn about this duality structure, of course, it immediately gives you a way to design algorithms. These are called primal dual algorithms. You can keep switching between two problems and try to get a faster algorithm. Okay? And that's what we're going to do next time. So this is for next Tuesday.